Have you ever wondered what makes a radio receiver tune into a specific station so clearly, or how certain filters precisely isolate desired signals from a noisy background? It all comes down to fundamental circuit properties that shape a circuit's response. Circuit bandwidth in relation to resonant frequency and Q factor is fundamentally defined by how selectively a circuit responds to different frequencies. Specifically, bandwidth is the range of frequencies over which a circuit's output power is at least 1/2 of its peak output power, often called the -3 decibel points. This bandwidth is inversely proportional to the circuit's Q factor, while the resonant frequency is the center frequency of this band. The core mechanism behind this relationship lies in the behavior of reactive components, inductors, and capacitors within an RLC circuit. At the resonant frequency, the inductive and capacitive reactances cancel each other out, resulting in minimum impedance for a series circuit or maximum impedance for a parallel circuit, and thus maximum current or voltage response. The Q factor or quality factor quantifies how sharp or selective this resonance peak is. A high Q factor indicates a very narrow bandwidth, meaning the circuit is highly selective and responds strongly to a small range of frequencies around resonance. Conversely, a low Q factor means a broader bandwidth and less frequency selectivity. To understand this practically, consider that the bandwidth of a resonant circuit can be calculated by dividing its resonant frequency by its Q factor. For instance, if you have a circuit tuned to 100 kHz with a Q factor of 10, its bandwidth would be 10 kHz. This means the circuit will effectively pass or amplify signals within 5 kHz above and 5 kHz below the 100 kHz center frequency. It is important to recognize that the Q factor is largely determined by the inherent losses within the circuit, primarily the resistance. Less resistance leads to a higher Q factor and a narrower bandwidth, making the circuit more efficient at resonance but also more sensitive to frequency changes. This principle is crucial in applications ranging from precise radio frequency tuning to designing highly specific filters in communication systems. Ultimately, understanding the interplay between resonant frequency, Q factor, and bandwidth allows engineers to precisely design circuits that exhibit desired frequency responses, ensuring clear signal reception, efficient power transfer, and effective noise rejection across various electronic applications.